Okay, welcome back to another video lecture for calculus. This video is designed to support a calculus course that I'm teaching this semester. Now in this section we're going to begin Unit 2, and Unit 2 is going to look at a lot of the different applications that we can use derivatives for. So in Unit 1 we learned how to do derivatives, we learned the processes, and now we're going to talk about what those processes can actually do for us and how they can be useful. But before we get into a lot of the applications and theorems, what we want to first do is discuss what exactly the point of doing a derivative in the first place is. And one of the easiest ways to kind of see how this could immediately be useful is with an application from physics. So in physics we know that if we take a mass times an acceleration, then that's going to give us a force. And in the algebra-based physics that most people have before being exposed to Cal 1, this is the equation. If you were to look at a calculus-based equation, then you're dealing with vectors instead of scalar quantities, but you know, the idea is not lost. It's still an acceleration times a mass that gives you a force. Now, one of the things that calculus is most useful for are functions that are in the time domain. And what I mean by that is that the units that are given to you will have some kind of time component to them. And so as we look at this expression, which is force is equal to mass times acceleration, we know a couple of things about the units. First off, force will be given to us in this Newton's unit. Mass will be given to us, and I believe the correct unit for it to be in order to produce newtons is kilograms. And acceleration will be something like meters over seconds squared. And you'll notice that we have this time change on the bottom. So it's got some element of time that we're dividing by. And one thing that we can note about this is that if we were to take some quantity, maybe x, and we were to say take a derivative in time, then what we get is a dx by dt term, and that just comes from the procedure that we would use in order to generate a derivative here. Now notice here that the dx dt term is like a small change in x over a small change in time. And so if the unit for x is being measured in something like meters and the unit for time is being measured in something like seconds, then that dx dt term will have a unit, meters per second, which is a unit of velocity. And that's an important notice because the position of something, which is sometimes x, sometimes y, sometimes it's just labeled s, it just depends on which specific textbook it is that you're reading. Its first derivative, you take a derivative of it, that's dx dt, which is equal to velocity. Okay, so notice that what velocity in the physics sense is defined as is a rate of change. It's the rate at which your position changes. And we can play a similar game with acceleration. If we take velocity and we do another time domain derivative, then that's going to give us this dv dt, which is the same thing as the second derivative of the position, because notice that we took a derivative of position to get velocity, so if we do a successive differentiation here, that is a second derivative of position, which is the acceleration, which is the rate at which velocity changes. And we note that the velocity would be given to us in something like meters per second, and the time derivative puts another second on bottom, and that cleans up as meters per second squared, like this guy up here. So a lot of these time-based functions, what you'll notice is that as you start taking derivatives of various quantities within the domain of time, what you actually are producing is a rate at which something changes. And so one of the first most immediate uses for derivatives is to express the rates of change of different quantities. And a lot of times we're able to take problems that have lots of little variables from, say, physics or geometry, and we're able to express these in terms of derivatives, which allows us to get to a point where we have some function of a single variable, t, which will stand for time, and then we have a bunch of constants that are just things that you have to plug in. For example, the mass, like it's just going to be whatever the mass of the object you're dealing with is, and then all I have to do is plug in time, and that will produce the quantity that I want, and that is sometimes easier than working out what the acceleration is through another algebra-based formula. So the derivatives allow us to kind of shortcut this kind of thing, because we can simply find what the rates of change are and then plug them in. And so a lot of times you'll see this Leibniz notation that is used for that. However, there is an additional fluxional notation which is sometimes used in physics, where the first derivative, which is the velocity, would simply be x dot with the little dot over the top of it. That's the first derivative of x. And acceleration, which is a second derivative in fluxional notation, will be this x double dot down here at the bottom. Okay, so one of the most important uses for derivatives is that we can express rates of change using derivatives. So if I want to note what the rate of change of something is, then I might be able to find a derivative that expresses that. And another place where this is very useful is when we get problems that we would call things like related rates, for example. So suppose that I have a leaky faucet and it's dripping water onto the floor, and I'm measuring the radius of this circular puddle of water as the volume increases, the volume of water that drips onto it is increasing. And so, for example, let's say I want to know how much area of the floor this is going to cover after how much time, or better yet, what the rate at which that puddle would be gaining area. If I know at what rate the water is increasing in radius. So if I know how quickly something is increasing in radius at a specific time, then I can work out how quickly the water is gaining area. And so we know that the area of a circle is going to be pi radius squared. Now, notice that if I take a time derivative of this whole thing, ddt of the whole thing, then over here on the left-hand side, I'm going to have derivative of area, derivative of time, and on the right-hand side, I'm going to have 2 pi r, and then I'll have the rate at which the radius is increasing. And so from here you can see I have the radius is increasing, and if I wanted to work out the rate at which the area was increasing, I could very easily plug in all the numbers that I know, and it gives me the area. If I wanted to work this in reverse, like let's say I know the rate the radius is increasing, and I know the rate that the area is increasing, and I want to know what specific radius it is that that's going to happen at, then I can plug in my numbers and solve for r. And it gives me some very useful formulas where I can take information that I have about the rates at which things are changing, and I can get specified quantities out of it, which is a very, very useful thing. Sometimes it is easier to measure the rates that something changes as than it is to measure the specific quantity itself. And that can be very helpful to us. It's one of the first uses for
derivatives.